That's why you had to do it.
Right, it had, yeah, to make it a calculus test.
Over?
Already gonna be bad on calculus.
I know.
All right, so spherical coordinates. We're going to represent points as rho, theta, phi. And I'll draw a picture here in just a second. Rho is the distance. I'm going to say, that'll be fine. Rho is a distance from the origin to the point. So this is, rho is like the radius of our sphere. Theta is the same as our angle in polar coordinates. And cylindrical coordinates. And in this case, in spherical coordinates, we're going to say that our polar r is greater than or equal to 0. So we're not going to have negative radii in spherical coordinates. And phi is the angle between the positive z-axis and the segment between the origin and the point. And in spherical coordinates, our phi is going to vary between 0 and pi. So we're going to let theta go from 0 to 2 pi, but phi is just going to go from 0 to pi. And I will get the entire sphere. So let's draw a picture. So there's our rectangular coordinate system. And here's a point out here in space. This is coordinates rho, theta, phi. And I'm going to draw the segment between the origin and the point. And I'm going to project that down into the xy plane, like so. I'm going to draw that segment is in the xy plane. And I'm also going to project over here onto the z-axis, like so. This angle is phi. This distance is rho. And this angle is theta. And this is a 90-degree angle here. So from this right triangle, we can see that, oh, and this is our polar r. And it's the same as this distance. So we can see from this right triangle that r equals rho sine phi. From this right triangle. And z, this side, is rho cosine phi. And that's going to be the key to our conversions. That our polar r is rho sine phi, and the z coordinate is rho cosine phi. All right, so emphasize a couple of things. Rho is always positive. Our polar r is always positive. Phi varies between 0 at the positive z-axis and pi at the negative z-axis. And allowing theta to vary from 0 to 2 pi is going to let us move around the entire sphere. All right, so let's look at our conversions. The conversions, this little right triangle here is the key to our conversions. And spherical coordinates are going to tend to be useful when we have some kind of spherical or circular symmetry about a point. So sometimes it's hard to tell whether or not whether spherical or cylindrical are going to be better in a certain situation. Usually if we have a circular symmetry about an axis, cylindrical coordinates are going to be a little easier to use. But if we also have a circular symmetry about a point, then spherical coordinates are equally as easy to use. All right, so our conversion, spherical to rectangular. X is r rho sine phi cosine theta. Y is r rho sine phi sine theta. And z is rho cosine phi. We want to go the other way, rectangular to spherical. Rho squared is x squared plus y squared plus z squared. Tangent theta is y over x, just like in polar or cylindrical. And phi, we're going to use this, is the inverse cosine of z over rho, square root of x squared plus y squared plus z squared. And again, that little right triangle that we drew is the key to these. And then we can go spherical to cylindrical. And we're saying that r, again, our polar r is greater than or equal to 0. Rho is the square root of r squared plus z squared. Theta equals theta, and phi is the inverse cosine of z over rho, square root of r squared plus z squared. But if you remember these, that's going to get you wherever you need to go. All right, questions? All right, let's look at some examples of some conversions. I'm not going to spend time converting points from rectangular to spherical. We want to just jump in and start converting equations. We want to go to spherical. X squared plus y squared equals z squared. So before we convert, what is that thing?
Hyperbolic, one-sheeted hyperbola, void.
There's only one negative sign. When you move the z over, there's one negative sign, so it's a hyperboloid of one.
In the xz plane, x squared equals z squared.
That's a line.
It's a line.
Oh, that's a cone.
Y squared equals z squared.
That's a line.
It's a line. So in the two coordinate planes, we get lines. And for a constant z, x squared plus y squared equals a constant, we get circles. So this is a cone. The hyperbolas come when you cut the cone parallel to the xz plane or the yz plane, because when we talked about conic sections, if you slice a cone parallel to its axis, you get hyperbolas. All right, so this is a cone. Let's do our conversions. X squared is rho squared, sine squared phi, cosine squared theta, plus rho squared, sine squared phi, sine squared theta, equals rho squared, cosine squared theta. Get lots of sines and cosines when you start dealing with spherical coordinates. When we start taking derivatives in spherical coordinates, you get lots of interesting things happening. All right, but what can I do here?
Take out factor.
Factor. We have a yes. Oh, sorry, this should be phi. Thank you, Sam. We can factor a rho squared sine squared phi. And we get cosine squared plus sine squared, which is just 1, equals rho squared cosine squared phi. I can divide by rho squared cosine squared phi. And I get that tangent phi equals plus or minus 1.
Do you get tan squared or tan squared?
We get tangent squared equals 1, so tangent is plus or minus 1.
Oh.
So I can add that step in here. Tangent squared phi equals 1, so tangent phi is plus or minus 1. Divided both sides by rho squared cosine squared phi. And sine squared phi over cosine squared phi is tangent squared phi. Did we lose the solution rho equals 0 by dividing by rho?
No.
Do we get the origin here? Is tangent phi ever equal to 0?
Yes. No.
Was this, does that line go through the origin?
No.
Tangent phi equals 1.
No.
Y over x equals 1. Y equals 1x. Does that go through the origin?
Yes.
Yes. Okay, thank goodness. All right, so we still get a point at the origin. All right. Well, let's go one step further. If tangent phi is plus or minus 1, what is phi?
Pi over 4.
Pi over 4 and
3 pi over 4.
3 pi over 4. The equation of a cone in spherical coordinates is phi equals a constant.
Is this a two-ended cone or just
Uh-huh.
double-lapped cone?
So what we're saying here phi equals a constant. So no matter what for any value of rho, we're at this value of phi, or this value of phi. Theta can take any value, so it can rotate around the z-axis. So for any, the phi stays constant, we rotate around the z-axis, and we trace out a cone. Down here, we trace out a cone. For any value of rho. Here, rotate around that theta value, varies from 0 to 2 pi, and we get our cone. So in spherical coordinates, phi equals a constant is the equation of a cone. Much nicer equation than x squared plus y squared equals z squared.
Is it? Oh, yeah.
And what does this pi over 4 represent?
The angle.
The angle that the cone makes.
It makes the angle in rectangular coordinates, what does it represent?
The slope.
The slope of the cone.
Yeah, this tells us the tangent of that angle tells us the slope of the line that makes the cone. So if we have a steeper slope or a smaller slope, then our angle phi is going to be bigger. If we have a steeper slope, then phi is going to be smaller. So the tangent of phi tells us the slope of the lines that make up the side of the cone. Yes.
So if it was theta in the constant, would it be a cone around the x-axis?
If we had theta is a constant
Yeah.
for any value, no, that would be a line, right? Because we'd be at a particular value of theta. Rho could be anything. Would that no, that would be like maybe a parabola or a hyperbola. Because you'd have, let me just get a page here.
So how would you make a cone around the x-axis?
You would have z squared plus y squared equals x squared, and you do your conversions that way. And then the equation wouldn't be as nice because this is about the z-axis. But if theta is a constant, that tells us we're out here somewhere at a constant theta. Rho could be anything, and phi could be anything. So we could do. I think we'd end up with something like that.
Wait. Oh, okay.
I think.
But if it went over there, then the theta would change.
No, it's going. This curve is parallel. Obviously, it's parallel to that line.
But it would be two-dimensional.
Yeah, maybe it would be. I think it'd be a plane.
Yeah, it would be a
I think it'd be a plane.
Yes.
If theta is a constant, you just get a plane.
No, it
Because
doesn't travel.
our radius could be anything, and our phi could be anything. So you could get a plane. Yes.
Yeah, why is the travel?
All right. How about this one?
You're not ready. Anyway, Kevin.
All right. What is? We want to go to spherical. So first off, what is this thing? Sphere. Sphere, radius, and origin or center. Center is 0, 0, 1. All right, so we're just going to substitute in here, just like we did before. Rho squared, sine squared phi, cosine squared theta, plus rho squared sine squared phi, sine squared theta. We know what's going to happen there. Plus, when we square z is rho cosine phi. When we square that out, we get plus rho squared cosine squared phi minus 2 rho cosine phi plus 1 equals 1. We can factor here, and the ones go away, and we get rho squared minus 2 rho Um, minus 2 rho cosine phi equals 0.
Yeah.
Can we keep factoring this?
How do you get show more steps?
Did I let me add a more let me add another step here.
Like maybe at least like 3.
Yeah. That's quite the range of logic. And that equals 3. You got that? All right, moving on.
It's ridiculous.
Hold up.
32. You don't have to avoid.
Um,
Yeah. Shut up, you quit lying to us. No, you fact the first part, then you have a row squared cosine 13 factor 18. I was just helping you know. Sure.
equals 0. All right, we good there?
Yes.
This is 1. We get a rho squared sine squared phi plus rho squared cosine squared phi minus 2 rho cosine phi equals 0. Now we can factor a rho squared out because we get a sine squared phi plus cosine squared phi. Rho squared minus 2 rho cosine phi equals 0. So we just used the Pythagorean identity twice. I'm going to factor, let's see, I'm going to write this as rho squared equals 2 rho cosine phi. And I'm going to divide by rho equals 2 cosine phi. Do I miss a solution rho equals 0 here? Because do we get, do we get a value of theta where rho is 0?
No.
Pi over 2. So when phi equals pi over 2, we get rho equals 0, so we don't lose that solution. So this is the equation of a sphere with radius 1, centered at 0, 0, 1. Do you remember in polar coordinates, what is, if we graphed r equals cosine theta, what do we get? A circle.
Let's do it.
Circle, radius 1, but about which axis? The x-axis, right? Because our reference axis for theta is the x-axis in polar coordinates. Our reference angle for phi is the z-axis in spherical coordinates. So this would be a sphere, like so. And there's our sphere. This would be 0, 0, 1. And in polar coordinates, we said that would be our circle in polar coordinates. So very similar idea. This should be a 2. There we go. All right, questions? Okay.
Tell me when it's time for some